It seems like people outside the tech industry think of computers and the programs they run on as one and the same, but in reality there's a huge difference between software and hardware. Any computer, your laptop, smartphone, probably even your car nowadays, is made up of billions and billions of tiny electrical circuits which us software developers could never dream of understanding in their entirety. Because when writing software nowadays, you're building upon layers and layers of abstraction. For example, when developing a website, you'll probably write code in JavaScript. There's actually a little bit more going on behind the scenes, but to put it simply, this code is interpreted by the browser, which runs on top of an operating system, which itself runs on top of the hardware. But it wasn't always like this. In the early days of computers, programmers didn't have so many layers of abstraction. Margaret Hamilton was one of these early programmers, and the work she and her team did helped pave the way for modern computing. Her family was not particularly wealthy, so in order to save money for college, she worked a number of different jobs throughout high school and college. When Hamilton graduated with her degree in mathematics, she worked for a meteorology professor at MIT writing software for weather prediction. There, she learned computer programming from scratch. Keep in mind, at this point, programming was literally done on paper. Code was often fed into the computer via holes punched into a paper tape. A programmer would use a device to punch holes one by one, and then a reader would take in this tape and detect the holes using a conductive metal brush. Hamilton went on to work on the Semi-Automatic Ground Environment System, or SAGE, at MIT's Lincoln Laboratory. SAGE was an early project of the U.S. Air Force which used computers to automatically detect threats via radar. At the Lincoln Laboratory, Hamilton continued to develop her programming skills, and by the time she was interviewed for a position on NASA's Apollo missions, she received 2 job offers. In fact, Hamilton didn't want to hurt either of the recruiters' feelings, so it was settled by a coin flip that she would work on the computer which flew aboard the Apollo shuttle. Hamilton worked on the overarching system of the Apollo computer. Various area experts or guests would work on individual components of the code, and Hamilton's team would integrate them together. One day, Hamilton was working on a new release of the software when she created a bug by mistake. Since she was working on the overall system, this caused everyone else's code to suddenly stop working. After everyone came to her asking why, she devised a new system. Everyone would write their own offline copy of the software, and it wouldn't be integrated with the rest of the code until the programmer was happy with them. Then, every day, all the programmers would receive a paper memo of what changes made it into the main version. As a quick side note, the people in charge of integrating all of the disparate elements were affectionately referred to as rope mothers. A major challenge in writing software for the Apollo computer was the ever-increasing memory requirements. Computers need a certain amount of memory where they can do their calculations, sort of like a scratch piece of paper, but they also need a place to store the program that they will run. For this memory, NASA used a type of memory made of hand-woven wires, which were originally designed for NASA's Mars probe. This was commonly called rope memory, and so the term rope mother was born. What really surprises me about these early Apollo stories is how clearly you can see the early versions of many software practices. Hamilton's offline and main versioning scheme sounds a lot like a modern version control, only today developers usually work on a version of the code that is literally offline, as in not on the internet. And the main version usually is hosted on a server somewhere. Then a separate piece of software automatically merges these versions together. Margaret Hamilton also talked a lot about the challenges of developing system code. Other engineers would come up with specifications and algorithms independently, and Margaret's team was responsible for putting it all together. They had to think not just about making the program work, but also putting it together without conflict. This is something I love and I think is sort of central to software development. When developing a piece of software, you're integrating hundreds or even thousands of components into one final product. It isn't just about creating the final algorithm that will do exactly what you want. It's about connecting hundreds or even thousands of puzzle pieces to create one meaningful product. However, in studying Hamilton's story, I can also see some of the roots of the more problematic elements of software development. The original specifications for Apollo's software were way off, and the requirements just kept growing. This is still a challenge in software development today, and it can lead to long work hours and eventually developer burnout. In addition, the 1960s were considerably different in terms of gender expectations. Women were very much underrepresented in engineering and especially in computer programming. Oftentimes, they'd be paid less than their male counterparts for no reason. Unfortunately, that remains true to this day. I really admire Hamilton's ability not to be fazed by people questioning her. While working on the Apollo missions, she advocated for herself and never let others shake her self-confidence. But she also recognized her own mistakes and learned from them. There's still a lot of progress that needs to be made in the tech industry, but stories like these make me proud to be a software engineer.